So you've got to lay this stuff in the beginning of chapter 4. They give you this stuff here. So just to make something up real quick. Oh, let's see. There. Okay. All right. And then how do you find the mean? What do you have to create to find the mean? What's the formula for the mean in this case? I always thought it was kind of nifty that the first 3 letters of the other name of mean, expected value, EXP. That's basically the formula for the mean, right? E sum XP. All right. So I make another column, x times p of x, because what's this formula say I need to do? Get a bunch of those and then add them up. So whenever you cover that summation symbol, that tells you what column to create, because I can't add those up until I got them. Okay. So I'm going to make an xp of x column. So then I get 0.2, 1.2, 0.7, 2.4. 6 point something? Really? 3.1? Whoa. No. Let's see. 3.1, 4.3, 4.5.
5 times 0.4 be 2?
It would be 2, Jeff. So then you're probably right. 3.2, 3.9, 6.3. Is that what you said? All right. I'll catch up to you someday. So the mean. So what's 6.3 is the sum of these. That's the mean. And then the standard deviation formula that we came with, the variance formula that we created last time, using our much beloved algebra a little bit. I didn't show every single step except for somebody stayed after. I showed them all the steps. It's not that bad, but it's also a little bit too much to get into. How that came from where we started. You guys remember we talked a little bit about that? I at least wanted you to see where this piece came from so you can buy into it a little bit more. So so what do I have to make a column of? I got to make a column of x squared p of x's so I can add them up. Right? That's what you can always do when you have a formula in your formula. So you cover the summation symbol. That piece tells you what column to create, so then you can add those up. So how do I make an x p of x? Well, it's x squared p of x. The way I do it might be a little weird. Weird? 5 times 2 is 10. I do x times x p of x. You could also do x squared times p of x. It comes out to the same number, because math don't give a shit what order we multiply in. They don't give a shit. So 6 times 1.2, 7 times 0.7, 8. I don't know if I trust myself anymore. Is that right? Yes. You guys with me? I mean, this is on that sheet I gave out last time, right? There are 2 problems in the homework you have to do the standard deviation for. I added that on there. So that I get 17, 21, 22.1, 41.3 maybe? 24.1, 31.3, 41, yeah, that sounds right. What do I do with this? What is this? What is this? I love you guys. You guys are like, it's 41.3, Jeff. But well, what is it?
Some of that.
The sum of x squared p of x. So wherever I see this, I replace it with that. So I see it here. So the variance is 41.3 minus the mean squared. And then this standard deviation will be square root of whatever the hell that is. .69. 39.69. Stop it, Jeff. I can't do it. It's too early trying to do all in my head. I couldn't even freaking do 5 times 0.4 earlier. What's my... All right. Is that cool? Is that all right? I mean, that's you're going to have the formula that we created sitting on a formula sheet for yourself. And then to remind you how to create the column, cover that and go, oh, I need an x squared p of x column. I do not need an x squared p of x minus mu. That doesn't make any sense. What is it saying? Sum up these and then subtract that. Because we know order operations, please excuse my dumbass son, it says to do subtraction last. Because it's at the ass end of PEMDAS. Yes, those are the things I say about it. Or like one of my algebra classes, they came up with this themselves. They said, please excuse my deficient algebra skills. They said that should be the saying for PEMDAS. Wasn't me. Yeah, it was you, Jeff. No, it wasn't me. Okay, is that cool? Is that all right? So it's 76 and 77, right? Those problems that I said on the sheet to also do the standard deviation for. Okay, maybe. Anything else from homework stuff? Chapter 4 stuff? No? All right. Man, you guys are extra oppressed today. I'm sorry. Statistics suppression. Okay. So this is going away. And we're going to get into section 4.3. This is a nice little review of 4.1 and 4.2. Yes?
How can the last problems in the quiz?
Say again?
Number 4 in the quiz.
Oh, yeah. So, number 4 on the quiz, I gave you, I can't remember, I think I gave you something like this. I told you all those things, right? And the first part it said, what's the probability of A and B? And of course, that's this times this. So when your formula is on your sheet, if you brought one for yourself. And then, then for part B, I say, what the hell is the probability of B? And I have a lot of people that say, I don't have a formula for that. Nobody does. Nobody in the universe. I do have a formula for this. And it's going to have in it probability of A plus the thing I don't know minus this thing I just calculated equals the thing I told you. That's an equation I can solve for P of B. You had to do that in the homework for in a few places. So they just use a little algebra to save our ass. Right. Algebra does what it can to help, believe it or not. Is that all right? Does that make sense? So you had to write an equation for one of the things I told you, because there is no equation really for P of B. But it does show up in the equation for this. And I told you what this is, so that gives you a way to solve for it. I like it. Which is the basic idea of algebra, right? Yeah. Working backwards to figure out something. Yes, no, maybe?
The second one, P and then B line A. What is that line?
Yeah, what's that line? How do you say that?
B
Given.
and A.
Yeah. So probably be given that A happened. Yeah, I like it. Okay. So remember I told you the thing that gets people down, there are no word problems in this class at all. You guys probably still disagree with me, but there aren't. The thing that gets people down are the symbols. The Greek symbols, the given symbol, all these little symbols, all this little shorthand that math people came up with because we're too lazy to write that much. And some of us should not be writing that much because we can't write too well. So it's better to have symbols. All right. Anything else from homework stuff or a quiz? Okay. All right. So what we're about to get into, there was a problem on the quiz that dealt with, some of you guys had, let me see if I remember, some of you guys had a problem about North Korea. Some of you guys had a problem about China. Some of you guys had a problem about, I can't remember now. Government being the most important problem facing the nation today.
Oh, you gave me the boring one.
Huh?
You gave me the boring one.
Oh, that's too bad. This is luck of the draw. All right? The one about North Korea wasn't that exciting. Sorry. It was just a little more exciting than the actual meeting that didn't really happen. But I ask you to do, let me give you one that everybody's got now that nobody had on the quiz. Let's say the probability that somebody thinks healthcare health chair, Jeff? Healthcare is the most important problem facing the nation. I looked this up, and let me see if I remember. I think it was like 6% now or something. Doesn't mean that nobody thinks healthcare is important. This is supposed to be, the question was, what's the most important problem facing the nation? And government was number one at 30 whatever percent it was. Right? On the same survey, 6% said healthcare is the number one problem facing the nation. And I ask you, what's the probability that the first three think it's a problem, while the last one doesn't? This should sound very familiar from the quiz, right? But I gave you a different situation, but same question. So I got how many people? 4 people. So I'm going to make 4 spots, right? I think the first, this guy, and this guy, and this guy, and then this guy thinks something else. So what's going to go in each one of these? 0.06, because this guy thinks it is a problem, this guy thinks it is a problem, this one thinks it is a problem, and then this one thinks it's not. So what goes here? All right, now, that's the way you should have done that problem. If you had 31%, it should have been 31, 31, 31, 69%, 0.69, right? Make them decimal so you get these funky-ass answers. Is everybody cool with this so far? Now, let me see if you guys can tell. What's the difference between this question and if I ask you, what's the probability that, so if I pick 4 again, it's probably that at least one doesn't think healthcare is doesn't think that healthcare is the most important problem. I don't want to write all that shit. Are you guys? What's the difference? This is a situation. How many people in this situation think that healthcare is not a problem? How many people think that healthcare is not the most important issue? The last one, right? Just one. Stay with me now. So here's a situation where one person does not believe healthcare is the most important issue. What is that question asking, though? Is that question asking this? This is way too specific. Here I said the first 3 think it is, and the last one doesn't. What else? What other way is there to do this? So let's say, let's give healthcare the letter H. That makes sense. So one way to do this is that the first 3 think it is, and the last one doesn't. But what other way is there to match what this is asking for? So how do we do a probability of OR? What's OR basically mean? Addition. If there's more than one way to meet what I'm looking for. So if I said, I need somebody who knows nuclear physics or somebody who's worked on a submarine. Either one. So I'm going to do all these plus all these, right? To get my probability. So if I said I need at least one, let me see. I'm being a little bit more evil than I wanted to be. Let's say exactly one. At least one would be horrible. We should know that by now. If I want exactly one who doesn't think that way, this is one way to do that. What's another way to do it?
Have the first one.
Yeah, or maybe it's the or. Let me do it like, or the first one doesn't think so. Or the second one doesn't think so. Or the third one doesn't think so. And I've already got the last one doesn't think so. Okay, so there's a difference. This is why I had to be very specific. A probability to get a blue chip and then a red chip. If I said exactly one blue chip, well, it could have been the first one was blue or the last one was blue. You have to add those together. So if I'm very specific, you don't have to do that yet. This last section now becomes more general. Not I want the last dude to not think so. I want exactly one. It could have been any of them. I like it. Yes?
So to answer that, would you have to do every single line and then add them up and then that's...
Well, here's the cool thing. What's algebra say about every single one of these?
They're the same.
Yeah, what's algebra say that they all look like? What is h times h times h?
H cubed.
H cubed. And then times d, right? They all look like that. And then how many of them are there? 4 of them. 4 of these. So look at this. What does this say? How many do I want to not think, doesn't think that that's true? 1. That's why it's a first power here. Which means I have 3 that think the other way. And how many total ways is there to do that? 4 total ways. Okay. All right, so let's set up another problem. That'll be a little easier to look at maybe. So what we're doing now, this first line is a problem we've done before. It was on the quiz. Now we're just kind of expanding the idea and saying, why has it got to be the last dude? Why not just let it be anybody? And then I have to add all those different situations. What's going to suck, and what we're going to use the calculator to do for us, why is this a 4 right there? It's not a big question. Why is that a 4 right there? Because there's 4 ways to do it. And I don't know if you guys have ever heard the whole idea about how many types of pizza can you construct from so many different toppings. It's like in the millions. Have you ever heard of that?
Yeah.
There are millions of different combination pizzas that you can put together. Have you ever heard, anybody ever played solitaire? If you have an office job, you played solitaire, so, right? Have you ever heard the idea that, and actually this is more general, anytime you shuffle a deck of cards a few times, it's really likely that maybe it's never happened before to be exactly in that order. Okay, I like it. So this whole idea is counting all the possible orientations of things. So really, why is that 4? Because there were 4 ways to have one person not think a certain way. It could have been the first person, second person, third person, fourth person. What's going to suck about these problems is what happens if that list gets stupid large. I don't want to have to make the list every time. So let's start off with a nice problem we can actually see, and then I'll go to a problem that the list would be way too big. So start with this. I know I like to go back to left-handed people. Probably somebody's left-handed is 11%. So it's probably they're not left-handed. 0.89. I love it. So for the ease of writing these, let's call this P, we'll call this Q. P represents the probability of success. So in this problem, I'm going to be looking for a certain number of left-handed people. So finding a left-handed person is a success. A success doesn't have to be happy. I could be on a battlefield looking for dead people. It's not a happy situation, but that's a success if that's what I'm looking for. Rabid squirrels, whatever the hell I'm looking for, finding that is a success. So I'm going to call the probability of success left-handed and the probability of failure not left-handed. Just so I can write these things a little bit quicker. So what's the probability? If I pick 5 people at random, what's the probability that I get exactly 1 left-hander? So we can create this list. This is not a very large list because I only have 5 people and I'm only choosing 1 of them to do something. So out of those 5 people, who could be the left-handed person?
Any of the 5 of them?
Yeah. So, for example, could be the first one's left-handed and the other 4 aren't. Or, get out of there. You already got to be left-handed. Or the third one. Or, thank God I didn't pick 7 or something. The 4th one. Or the last one. So this is not going to be a part of our work. I want to do it right now so you can concretely see what's happening. You can see where this number is coming from. It's the length of the list. If only we had something that costs like a lot of money because it's able to count shit. Oh, we do. Calculate. So we're going to get that list length. We will eventually start getting it from the calculator directly because when it starts to get in the millions long, I don't want to list them, right? But right now, it's not bad. So algebraically, what does all this come out to be? Algebraically, what are each of these? It's this p times q to the fourth. And of course, I have how many of them? 5. So I have 5 p times. Now, why does this make sense? Why does it make sense that this is a first power here? Because p is a success, and how many successes do I want? 1. Which means how many failures must I have each time? The rest. This formula is almost too nice to believe. The funky part of it will be the one related to that number. The rest of it is just really nice. One of these, 4 of the other ones, because it says exactly 1. So if it said exactly 2, what would this have been? 2, and this would have been 3, because you got 5 people. 2 of them are this, 3 of them have to be the other thing, right? Maybe. Notice I was really careful, said not lefty. I didn't say right-handed, because, again, there's a lot of situations we got to take care of. That takes care of every situation. Okay, maybe. So, if we do the work here, so probability exactly 1 left-handed. 5 times p times q to the fourth. P was 0.11, q is 0.89, and then you just got to throw that in the old calculator. So how long of a list do you think you get in other situations? But real quick, anybody do this yet for me? Anybody got this? .3, isn't it?
0.617.
617 sounds big, but maybe I'm wrong.
I got like 3, 4, 5, 1.
Sounds better. 3, 4, 5, 1?
3, 4, 5, 1.
3, 4, 5, 1?
3, 4, 5, 1.
Yeah, that's what I got, roughly. Double check. I don't know if I trust my brain too much today. Let me double check 2. Yeah, 3, 4, 5, 1. I like it. Kick ass. So, this is if I have 5 people and I want to choose one of them to be left-handed. And why do I multiply here? Because it's the first one is left-handed and the second one isn't, and. Or this other situation. So or means add. And each of these is going to look exactly the same algebraically, because they each have exactly 1 p and exactly 4 q's. That's why the formula kind of breaks down into successes, failures. This number will be how long the list would be, because that's how many of those you're going to end up with. Okay, maybe. So how long would the list be, do you think, if I had 30 people and I wanted exactly 4 to be left-handed? Just take a guess. If I have 30 people, so it could be the first 4 or the last 4 or the middle 4 or the first one and the last 3, or how long do you think that list would be? Just give me a guess.
Exceptionally.
Huh?
Exceptionally.
Exceptionally. So one guess is exceptionally. I like it. Somebody give me a number guess. Just give me a guess.
30.
30? Give me a guess. Anybody else? So 30 people, and I want exactly 4 of them. So I could have the first 4, or the last 4, or the first 2, the middle one, and the last one.
Say 40 times 40?
Say again?
40 times 40?
So maybe 900?
Yeah.
I like it.
30 factorial.
30 factorial, okay. All right. Somebody's thinking. Of course, some of us are like, what the shit's factorial? Factorial is nifty. 30 factorial would be 30 times 29 times 28, all the way down to 1. So that's what that exclamation mark means if you ever see that. It's a nifty way to kind of, that comes up more often in math than you might think. So if you saw a 5 factorial, it'd be 5 times 4 times 3 times 2 times 1. That's what that 5 factorial is. That's the number that it is. I like it. Let's check it. Let's see. Just use my calculator, I think. Computer. All right. So where this is going to be, oh my gosh. It's a little zoomed in.
Hello.
Okay. So the way I'm going to put this in, this is kind of nifty. How would I say this in English? I have 30 people. And if I'm going to construct this line, I have to choose 4 places to put left-handed people, right? Every time I want to construct a situation. So I can have a situation where the first 4 are left-handed and the others aren't. So I chose the first 4. Plus another situation where it's the last 4. Another situation. So I got 30 people. I need to choose 4 of them. So that's what that notation means. Yeah, so it's not quite permutations. So 30, choose 4. It's what's called combinations. We're not going to get that deep into counting theory in this class, unfortunately. So here's how you put it in the calculator. You guys, I got more calculators if anyone needs them. So 30. Then hit the math button. Go over to probability. Yours might just say PRB. I don't know. And then which one looks like what I want? Yeah, not National Public Radio. Do NCR. So 30, choose. Now if you have an older calculator, it just says 30 NCR and you just put it in. This is going to look more like the way it looks in real life. 30, choose 4. Let's see how big this list is. 27,405. So if you tried to make a list that put 4 left-handed people everywhere they could be, within 30 people, you'd have a list that was 27,405 people big. I don't want to do that shit. But do I have to do that? What was the only reason I had to do that right here? We didn't know this yet. So I had to figure out how many ways, 5 of them to do this. And then we can get the probability, right? Well, now the calculator can calculate how long the list would be. What do we have to do? We still have to do something. So if I want the probability exactly 4 lefties, that would be 30, choose 4. So you got 30 people. I want to choose 4 of them to be left-handed. Times, how many of these do I want? Where'd it go? 11%. How many 11%? How many lefties? How many successes? 4. So how many failures does that leave over? If I have 4 lefties, I must have how many not lefties? 26. 11. I don't think I'm explaining this as good as I've ever done, but I really want you guys to get how simple this formula is. You got 30 people. Choose 4 of them to do the thing. Why? Because it said so. So I got 4 of these, the rest of these. So then you just got to throw all this shit in your calculator. So let's see. So if I do 30, choose 4, I got it right there, times 0.11 to the 4th, times 0.89, get out of there, 0.89 to the 26. So almost a 20% chance. So 0.193, where do you go? 9. So like almost a 20% chance you'll have exactly 4 left-handed people. This leads into, can you see how this type of math, if you're going to set up a classroom, And you know that 11% of the population is left-handed. How many left-handed chairs do you want to put in the classroom? Now, in this case, we're set. And with those new chairs, funky-ass, way too adjustable chairs, you can turn that sucker around, which is nice, but the thing doesn't want to stay anywhere. I don't know if you've ever been in those chairs. You know what I'm talking about? They're a little insane. Still, this is kind of leading into, this would also lead into how many extra plane tickets do you sell over the number of seats in your plane so that you have fewer planes with empty seats. I mean, if you're an airline, what are you going to do? You're going to try to pack the planes because you're going to fly anyway. Might as well get as much money out of this flight as you can. And that's why things like Priceline and Kayak and all those other things, not Kayak necessarily, those ones that do last minute things, they want to sell those seats. They want to make some money, so you might get some good deals on those sucky seats that are left over, right? If you do one of those things. You with me? You know, I don't care if it sucks because I'm going to just knock myself out and sleep. That sounds good. That's what I do. All right, maybe. Okay, let's do another problem. You didn't see any of that. We'll do it again. All right. Yeah. So let's say the probability people like liver. Who in here anybody likes to eat liver? With some fava beans? Nice Chianti? No? Silence of the Lambs? No? Okay. So probably somebody likes liver. Let's say it's 17%. I like it. So if I pick, what you got, Jeff? 63 people. What's the probability that exactly, get out of there, exactly 11 like liver? Become a K. There you go, buddy. So this formula, I'm going to set it up based on what we've done, and then I'm going to write it in general. And when you write a formula in general, it looks a little worse than it actually is. So how would I set this up? How many people do I have total? And how many do I want to choose to do something? 11. The probability of success is 0.17. How many of those do I want? 11. It's a little repetitive, right? 63 choose 11 to do something. So how many do this? 11. So how many do, what's the other thing going to be?
83.
Yeah, 8-3. Why? What's always got to be true about P plus Q?
100.
Has to be 1.
Or 100%.
P is something, Q is not that thing. They always have to add to be 1 or 100%. Does that make, it should hopefully make complete sense, right? Two types of people in the world, those who think you can break people into two types and those who don't think you can. Think about that. All right. So how many goes here?
52.
52. I like it. Try to plug that in your calculator. See what you get. I'll do it offline here. Come here, you. Are you still going? Yeah. Anybody want to tell me what they got?
Wait, 1307?
Cool. So just over 13% chance of that happening. I like it. So if I bought like 11 pieces of liver and I got 63 people coming and I'm like, what's the probability that they're going to eat all the freaking liver? There's a 13% chance that you'll have all of exactly eaten. So you don't have too little and you don't have too much because you're like, I hate liver. I don't want this in my house. I want it eaten and gone. Maybe. By itself, what we've done so far is not as powerful. What's more interesting would be the probability that at least 11 people like liver. then you can see if that's high, I'll probably want to buy more liver, right? Or the probability of that at most 11. Either way. Okay, all right, maybe. So here's what the formula looks like. Let's give these things letters. We already know what 63 is as a symbol. What letter goes with 63? N. Total number. Thank God. This is what I could change from question. I could ask another question and say, what's probably exactly 7 of them like it now? So that should get the letter X. So N is the total number of things you've got. X is the number of successes you want, because X is the thing that can change. That's the variable. I could have 0 successes all the way up to 63 successes. Okay. And then P and Q are just the probability of success, the probability of failure. So what's this formula look like? N choose X. I know the calculator uses R. Oh well. P to the X, I want this many successes. Here's what looks really weird. Where the hell did 52 come from? Yes, this is the part that looks really weird, but like I said, formulas have to be more general. They sometimes make it look worse than it really is. So people freak about this piece, but that just means the rest. If X do this, the total minus X must do the other thing. Oh my God, I've talked enough. Let me give you guys a little worksheet to try. Stay with me. Oh, you missed all that, didn't you? There you go, buddy.